Good afternoon everybody and welcome to the second part of this module on testing of concrete. So in the first part that we had a couple of days ago, we were talking about what are the different test methods to monitor the fresh concrete properties. We talked about some conventional methods like the slump test, the compacting factor test, the VB consistency test and so on. And then we also took a look at some specialized test methods that are applicable to highly flowable concretes like self-compacting concrete. Now what came across in those methods was the fact that the closer you get to the fundamental characteristics of the material, the better is the understanding of the flow properties. So here what we have been discussing so far deals with some standard and some non-standard test methods to determine the properties of concrete in the fresh state, particularly the special types of concrete that are flowable or self-compacting. We also briefly saw how rheology can be directly monitored using expensive equipment like rheometers. However, the use of modified simple test methods is far more important from a construction perspective because that can be done regularly on construction sites without really any problems. We then went on to understanding how we can monitor transition of concrete from the fresh to the hardened state, essentially how to track the development of setting and strength development. We saw briefly two different types of methods that were applied for the same. One was the maturity method where we are simply estimating the change in temperature of the system with respect to time. We calculated the area under the time temperature curve and defined that as the maturity of the concrete, and the assumption here was that any concrete that is at the same level of maturity should also possess the same level of strength or mechanical characteristics. So using maturity method, one can with the simple measurement of the temperature of the concrete figure out what the rate of strength development of concrete on site is. Okay. And then the other aspect was to look at strength development by the use of ultrasonic pulse velocity method. However, what we went on to discuss was that it's not just the velocity that is important, but it's the overall ultrasonic energy that is getting transmitted through the system. That is of prime importance because you can link it very directly to the growth of the structure within the concrete, and it seemed to be linked quite closely or depended quite closely on the total energy that was the compressive strength that was getting developed in the concrete. So compressive strength could be predicted with the measurement of the total ultrasonic energy that is transmitted through the concrete, because that tracks very clearly how the concrete transitions from a fluid state to a semi-solid to a completely elastic solid type of state. Okay. We then closed off the lecture last time with a brief discussion on hardened concrete. We essentially looked at some specifics of the fact that concrete, we are primarily only interested in compressive strength, and we also briefly reviewed the kind of factors that are responsible for determining the compressive strength, that is water cement ratio, cement content, type of aggregate, curing, age, ambient conditions and specimen geometry. And we looked at this simple relationship that people often prescribe for water cement ratio to strength, and this is qualified as the Abrams law. Unfortunately, this law, it's just an indication that compressive strength decreases with an increase in water to cement ratio. There is nothing universal about this. The other aspect was the fact that strength depends a lot on the porosity that is developed in the systems. The more porous your concrete, the less strong it's going to be. Okay, and what we also sort of took a look at was when we have different types of aggregate, there's a major mismatch in the properties of the aggregate and the cement paste, which leads to lower concrete characteristics than you would get if you had a better combination of cement paste and aggregate. But please remember, oftentimes with respect to aggregate, we are definitely limited with what we have locally available. Cement we can change in a project, but the aggregate has to be from the nearest possible quarry, because otherwise the cost of the construction can be tremendously high. So irrespective of what aggregate we have, we need to make concrete, and we need to work through the understanding of how aggregates and cement paste together behave, and we have to understand how, what kind of role this actually plays in the actual mix design process itself. As you all know, mix design means that we are trying to achieve a combination of workability and strength. Increasingly nowadays, we are looking at mix design to also look at durability of the concrete. We need to look at how concrete performs in a given service environment. Okay, so with that introduction, let me get into some aspects of compression testing that you really need to think about in more detail. Before I go to the specimen geometry, I'll come back here to the aspect of the aggregate itself. Now, many of you would have broken concrete cubes in the lab. I don't know how many of you have actually paid attention to the kind of cracking that actually appears in this concrete cube. You might have seen that the crack actually tends to propagate around the aggregate rather than through the aggregate for concretes when you are testing concretes of strength about 30-40 megapascal. Okay, what does that suggest? That suggests that most of your failures are occurring in the zone which is the bonding zone between the paste and aggregate. In concrete technology, we often refer to this as the interfacial transition zone. Okay, so now the ITZ is the weak link, and that is quite apparent from this simple schematic that I had presented in the last class, where you see that the cracks around the aggregate start growing at very low load levels. Even at about 30% of the load, you have substantial cracking around the aggregate, and that comes about because of the mismatch between the aggregate and paste properties. Okay, now if there is already cracking existing because of different factors such as shrinkage, such as thermal stresses, so on and so forth, these cracks are definitely going to grow more and more. That means the cracks in the interfacial transition zone keep growing more and more. Ultimately, these cracks grow into the surrounding matrix and develop into one large system of cracks. So what does this mean? This means that your concrete has a gradual route to failure, where the cracks first start growing around the aggregates and then propagate into the surrounding matrix. Now, what would happen if I increase the strength of my system? Okay, for example, if I am lowering my water to cement ratio to increase the strength of the cement paste that is surrounding these aggregates. So what am I doing? By increasing the strength of the paste, I am essentially getting my aggregate and paste quite similar in terms of its mechanical characteristics. So in other words, there is no longer going to be a mismatch between the aggregate properties and the paste properties. Both are going to have very similar stiffnesses, as a result of which when we start loading, the cracks are no longer going to form at the interface, but they may start first forming in the matrix. And these cracks, because the interface is so strong, will not go around the aggregate, but they may end up going right through the aggregate. Okay, so if you have tested high strength concrete in your lab, or if you are going to be testing high strength concrete in your lab very soon, just take a look at what the fracture surface looks like after the test is completed. You will see that the failure that you have see for the high strength concrete is explosive. That means you have chunks falling off, and you will often see that the crack has gone right through the aggregate. Okay, so very important distinction. Normal strength concrete, you have a gradual development of cracking. Cracking develops around the aggregate in the interfacial zone. In the high strength concrete, there is a very sudden crack that appears at very large load levels, and you have a failure that goes right through the aggregate. So essentially that means that your normal strength concrete or low strength concrete is ductile. I wouldn't say ductile like metals, but it has some degree of ductility. On the other hand, high strength concrete becomes more and more brittle. Okay, now very often you use different types of specimens to determine the compressive strength. Sometimes we use cubes, sometimes we use cylinders, sometimes we use even prisms to determine compressive strength. Okay, one important characteristic that you have to understand is, depending upon the type of specimen that you choose, you may actually end up getting very different strength results. Okay, not just the load, the strength itself would appear to be different. Does that mean that the material is different? No, the material is the same. I have used the same concrete, filled it up in a cube and a cylinder, but when I test it at the same age, I end up getting a different strength. Now, why is this happening? To do this, to understand this, we need to go back to something that you might have learnt in basic mechanics. Okay, there is something called the Saint-Venant's principle. Okay, Saint-Venant's principle. Now, as per the Saint-Venant's principle, the conditions at the end effects which are felt by the specimen will be felt up to a distance which is equal to the least lateral dimension. Okay, let me just explain this in a little bit more clarity. Okay, you can see this cylinder here, which has a length of L and a diameter of D. You are applying a load, uniaxial compression load. So you have this P load on top and bottom. Okay, so you are basically compressing the cylinder. So what I am saying is whatever effects are there at the end are felt up to a distance of d, which is the lateral dimension of your specimen. So until this distance you have the end effect, that is basically your compression as well as any friction that may happen between your specimen and the loading platen. Please remember you are loading this specimen inside a machine. So you have a top and bottom platen in the machine which are basically closing in on the specimen and then transferring the load, okay. So there is obviously going to be some friction between the material of the platen and the concrete surface itself, okay. So how is this friction going to help or going to affect the strength performance? So what do you think happens when you start compressing something? You know very well that when you start compressing something, it's going to bulge outwards laterally, okay. There's going to be bulging out laterally, okay. Now in the case of concrete, you know very well that it has a Poisson's ratio of close to about 0.18 to 0.2, okay. So you know that when there is an axial strain, there's obviously going to also be a lateral strain depending upon the Poisson's ratio. Now this lateral strain, when it exceeds the tensile capacity of the concrete starts developing cracks, okay. So although we say that we are testing concrete in compression, actually it is failing in tension, it is failing because the lateral tensile capacity is getting exceeded by the amount of bulging that is happening of this concrete specimen, okay. So now imagine that you are loading this cylinder in between two platens, so there is friction at the top and bottom. So what is this friction going to do to the specimen? So the specimen is trying to move outwards, that is trying to bulge outwards. I will just show this to you in a diagram that I draw on the screen on the board. So this is your loading platen, that is your bottom platen, that is your cylinder that is now getting loaded, okay. Now the cylinder wants to try and move outward, it is trying to bulge out because there is lateral expansion that is happening because of the compression in this direction. Now what does the platen and what does the friction at this surface do? If your material is trying to move outwards, the friction will obviously move inwards. The friction is trying to move the specimen inwards. In other words, it is opposing the effect of your lateral expansion. So what will it do to your strength? It will end up actually increasing the extent of strength that you have because it is preventing this bulging out. So it is delaying the failure of your concrete specimen, okay. So the end friction is delaying the failure of your concrete specimen. That means that the strength that you get in this region here, which is equal to a distance of d, d being the diameter of your specimen, the strength of the concrete in this region is actually going to be overestimated. Similarly at the top, okay, again that is d, the strength at the top and bottom are going to be getting the effects of the friction at the ends also, that means they are going to be overestimated. However, there is a zone in the center where the end effects are not being felt at all, okay. So here the zone in the center now has a perfect compressive sort of a loading, okay. So in other words, if you look at the strain distribution across this surface, it is going to be perfect compression, okay. That is a strain distribution. If you take a cross section along this line, you are going to get a perfect compression in this case, okay. So in a cylinder, because the L by D in a cylinder is always equal to 2, there is at least a very small infinitesimal zone right at the central portion of the cylinder where you have a perfect compression, where the friction effects from the ends do not seem to make any difference at all. What does that mean? That means that my specimen will now fail at the true compressive strength of the material. So cylinder strength is the true strength of the material. What about a cube now? In a cube, if you think about L by D, all the dimensions are the same, right? In the case of a cube, for a cube, L by D is equal to 1 because L, you have the same dimensions on all sides, right. So L by D is equal to 1 in the case of cube. That means that all through your specimen the frictional effects are going to be dominant. In other words, your strength of the concrete will end up getting to be overestimated as compared to the pure compressive strength, okay. So generally cube strength is about 25% more than the cylinder strength. So if you test cubes, you will probably get 25% higher strength than the cylinder, okay. So I hope you are able to understand the distinction as to why we get a higher strength from a cube than a cylinder. In simple terms, the frictional end effects tend to increase the strength of your concrete, okay, and that increase in strength in the case of a cylinder is not felt because you have a zone right in the center of the cylinder where there is no effect of the friction. In the case of a cube, the effect is felt throughout the depth of your cube because all the dimensions are equal, okay. So now if you think back, some of you might have done design of reinforced concrete structures. When you want to determine the capacity of a column in compression, you always take FCK and multiply it by a factor of 0.8. That factor of 0.8 is essentially to account for changing it back to cylinder strength because you want the cylinder strength which is the true strength of your concrete. So since the cube strength or FCK is higher than the cylinder strength, you have to convert it back to the cylinder strength. That is why you multiply FCK by 0.8 to ensure that you are getting the correct strength in compression in the equation to calculate the compressive capacity of a concrete column, okay. So specimen geometry or type of specimen has a major role to play in the ultimate performance of your concrete, okay. So coming back, I have described the same thing on the slide here. On the slide again you see the cylinder which is being loaded and there is a zone right in the center which has a pure compression, okay. In the case of a cube, the end friction is being felt all over the place. So you can actually even look at the failure surface, compare between cylinder and cube, and that will exactly tell you why this is happening. You can see in a cube that the failure surface is almost coming at 45 degrees from the edges and you get some sort of a pyramidal shape of failed concrete specimen from the cube. In the case of a cylinder, you may be able to still make out some vertical cracks towards the center of your cylinder, okay. Now in the cylinder itself, if you keep increasing the length beyond L by D of 2, or if you reduce the length so that L by D is less than 2, then obviously your strength is going to get affected. Now I am sure you will understand that when you increase the L by D greater than 2, what will happen is you have a greater zone now which is subjected to compression, so strength is going to actually reduce. As you see in this diagram here, produced from a book by Adam Neville, which I suggested in the last class was a very useful book to buy. So you have the strength plotted against the length to diameter ratio. So this is L by D of 2 where the relative strength is 1, that means your 100% strength at L by D of 2. If you increase the L by D to 2.5, 3, 3.5 and 4, you see a gradual reduction in your strength, and that is because you have a greater amount of zone where compression, true compression is actually acting. If you reduce L by D to less than 2, you see there is a drastic increase in your strength, and if you go to L by D of 1, you see that your strength is nearly 20% more than your strength of the cylinder with an L by D of 2, okay. So that L by D of 1 is approximately equal to that of a cube, okay. So 20 to 25% higher strength is what you ultimately end up getting with this, with the cube as compared to the cylinder, okay. So always remember this because this has a very significant role to play, because we use cube strength to determine our characteristic compressive strength which is FCK. To convert this back to the cylinder strength, we have to multiply it by a factor of 0.8, and that is what is done in your compression design for reinforced concrete structures. Okay, moving on, we are now going to talk a little bit about a property of concrete that we consider to be not very important in the case of typical concrete structural element design, but when it comes to something like flooring or pavements, the tensile strength of concrete is also extremely important. And further, we need to understand the effects of shrinkage and creep, at what stage would they be able to cause cracking in the concrete? For that we need to get an estimate of the failure strength of concrete in tension. So again, generally people suggest a relationship that the tensile strength of concrete is about 1/7 to 1/10 of its compressive strength. So we are not really accounting for very large strengths as far as tensile resistance is concerned. Okay. There are three common methods that we typically use to determine tensile resistance. One is direct tension, the other is split tension, the last is flexural strength. So let us take a look at these three techniques. So in the direct tension test, what you need to do is come up with a concrete cylinder or a prism that is gripped at both ends, and then you are simply trying to pull it off. So this is your prism that is gripped at both ends and you are trying to pull this off, just like in a steel. In the case of reinforcing steel, you have a mild steel or a deformed steel bar which you grip in the hydraulic grips of your testing machine and you simply pull it apart in tension. In the case of concrete, it is not all that simple, because you can imagine that concrete is aggregate and the kind of force that you need to apply to actually keep it gripped at the ends may be large enough to actually cause local crushing before you actually cause the failure of your prism in tension. Okay. To avoid this kind of a problem, people have suggested other things such as fixing the concrete prism to the top and bottom platens using some high bond strength material like an epoxy. Alternatively, you can test the prism with a notch in the center, so that you are overall going to be reducing the effective cross sectional area that is going to be taking the load. Okay. So that will help you determine the loading without actually failing the concrete at the top and bottom. These are alternatives that are possible, but please remember, tensile testing of concrete is a very difficult thing to set up. It is not easy to understand how to do this experiment, because designing grips for holding concrete in tension could be quite tricky. So because of this, we have alternative test methods that we typically use. The common one is your split tension test. Okay. This is an indirect method. So what we have here is a cylinder of concrete that is actually under compression. You apply a line load at the top and bottom. That is the line load at the top and bottom of your cylinder that is applied to the cylinder, where the cylinder is actually made to lie down, and you apply a line load on the top and bottom. And what if you look at the distribution of stresses across the diameter of your concrete, you will see that while the top and the bottom of the cylinder are in compression, there is a zone of uniform tension in the central part of the cylinder. There is a zone of uniform tension. Now the zone of uniform tension is what causes the cylinder to exactly split, okay, into two. Okay. So it is like a splitting test in which you are splitting the concrete cylinder into two halves. Okay. So this is actually your indirect tension test, because you are actually applying a compressive load, but the specimen is failing in tension. So here you can calculate by appropriate mechanics, you can calculate the tensile strength as 2 times the load applied divided by pi times the length into diameter of the specimen. Okay, 2 pi p by pi LD. And this is also called the Brazilian test, because it was determined or developed in Brazil by certain researchers, and it is a very popular test because it does not involve again any equipment where you need to apply a flexural load. Here you are just applying a simple compressive load. Okay. Now obviously the bending behavior of concrete is again a matter of great interest, so people try to determine the flexural strength of concrete also. This is probably the most common method of testing if you want to get a direct understanding of the flexural strength of the concrete. There are two arrangements which are typically used. One is called the midpoint arrangement, because here the load is exactly at the midpoint of your span. So that is the supports at the two sides, and that is the midpoint of the span. The second case, we call it the third point loading arrangement. The third point loading arrangement is when you have your loads at exactly L by 3 from the span. So L is a span, so L by 3 from the support you have the load, and here also L by 3 from the support you have one more load. Okay, so that is your third point arrangement. So there are several distinctions obviously. If you plot the bending moment diagram, you will see that bending moment and shear force diagrams, you will see that in the central part of the third point arrangement you only have bend moment, you do not have any shear strength, shear force, there is no shear force, okay, there is only bending moment here. So actually we tend to prefer the third point loading arrangement because we have a zone of pure bending and absolutely no shear. Okay. So, stress at which the first crack appears is also known as the modulus of rupture, and using the beam bending formula which all of you know very well, we can calculate the stress as moment into y, which is basically your distance from the neutral axis divided by I, which is the moment of inertia. Okay. So, based on the different type of loading arrangements, you will actually end up getting a different equation for your stress at first crack. Okay. And you can easily calculate based on the load at which crack appears what is your strength of the concrete. Please remember, when the first crack appears in a plain concrete, that crack is going to propagate very quickly towards failure. On the other hand, if you have a special system like a fiber reinforced concrete, the first crack does not mean failure, because after cracking appears, the fibers will start taking the tensile loads, and once the fibers start taking tensile loads, it takes some time before this crack can actually further propagate. So, in other words, fibers tend to help in the reduction of the crack propagation once the crack appears. Okay. So, in the case of fiber reinforced concrete, you will probably need to apply a slightly different technique where you will have to study what happens even after the first crack appears. For normal plain concrete, which we are testing for a mixed design, for example, we do with plain concrete, and in that case the first crack load is the only thing that is important, because the concrete specimen does not remain after that, it just splits, it breaks into two halves. Now, there are different characteristics of the concrete which may affect the compressive and tensile strengths. Generally, the aggregate interlock and good gradation of the sand affect both the compressive and tensile strengths, and in general, when you have better aggregate interlock, the ratio of the tensile to compressive strength tends to become higher. Okay. So, with age, however, compressive strength keeps on increasing, but flexural strength does not need to necessarily increase at the same rate. Okay. Generally, you should remember that with age there is probably more increase of compression than of tension, because essentially tensile strength is also affected badly by any cracking that is there in the concrete. The compressive strength is not as badly affected by cracking. Okay. Most codes would suggest a relationship of the form where tensile strength is equal to some constant multiplied by the compressive strength to the power of half, or square root of compressive strength. Now, please remember, this is only an empirical relationship, it has got absolutely no fundamental basis whatsoever. Okay. This is absolutely just empirical data fitting essentially. So, the data that you have for your set of concretes may or may not follow the same relationship. So, do not believe these relationships blindly, they are just a means for suggesting some equations to use when you do not have the necessary capability to conduct a test. Okay. As far as possible, the test should be conducted to determine the actual properties rather than to use these kinds of relationships. Now, we talked about like compressive and flexural strength. The next important engineering characteristic of concrete is the modulus of elasticity. Okay. Now, with steel, with mild steel especially, we have a very nice and linear stress strain diagram in the elastic region, because of which we are able to determine your modulus without much difficulty. However, in the case of concrete, you do not really have a highly linear sort of a behavior, especially in compression you get a lot of non-linearity, and most of this non-linearity actually arises because concrete is not a simple mixture of cement, paste and aggregate. You also have the effects of the interface or interfacial transition zone, because of which you may have a lot of changes in your concrete with time. So, for concrete one needs to be a little bit more careful in defining what is the correct modulus of elasticity to be used. So, what I have plotted here is the typical stress to strain behavior of concrete, that is plotted with this darkened line here, that is your stress strain behavior. You see that for the most part the stress strain behavior is non-linear, because of which it becomes very difficult to actually pick out a single value for your modulus of elasticity. What does the non-linear stress strain curve mean? That your modulus is actually changing, that means the stiffness of the system is actually changing. Why? Because concrete keeps on cracking. When your concrete keeps on cracking, the stiffness obviously is going to change or reduce actually. Okay. So, there are different ways of actually taking up your modulus of elasticity of concrete. What codes suggest is that we calculate what is known as a secant modulus. Secant modulus, basically that is the line drawn from the origin up to a point which is at about 33 to 40% of your ultimate load. Why that? Because we assume that in that regime up to that load level the concrete is still in the elastic region. We assume that concrete is still in the elastic region. So, what we do is we measure the strain when we apply a load level of about 30 to 40% of your ultimate load, and then what we simply do is we take the slope of that line which is drawn between the origin and the point at 30 to 40% of the ultimate load. That slope is basically our secant modulus or static modulus of elasticity. Okay. We can also take, because this is a non-linear curve, we can also take the slope of a chord drawn between any two points. Okay, that EC which is shown here, which is basically the chord modulus, is the slope of any line drawn between the any 2 points on the curve. That is called a chord modulus. Alternatively, we can also take the tangent to the curve at any point and call it as a tangent modulus. Okay, as per the codes, what we are supposed to use is a secant modulus. The tangent modulus and chord modulus give us some sort of an estimate about how the system is actually changing or increasing cracks, how are they reducing the stiffness of your concrete. For all practical engineering purposes, we assume that the modulus is simply the secant modulus. Now again, just like your compressive strength to flexural strength, there are also relationships suggested by different codes which link your modulus of elasticity to the compressive strength. Again, all these relationships have been proposed to ensure that you have a means of calculating your E modulus if you are not really having the wherewithal to test the E modulus. The testing for E modulus is a little bit more complicated because we are trying to now measure strain in the concrete specimen. Now, you can affix strain gauges or you can use what are known as compressometers for that purpose. So, again it is a little bit more involved as opposed to a simple uniaxial testing of the compressive strength. So, very often codes give these relationships for us to understand how to calculate the modulus of elasticity. So, as per the ACI American Concrete Institute equation, the modulus of elasticity is equal to 33 times the unit weight of the concrete to the power of 1.5 multiplied by the square root of your cylinder strength Fc. In the case of Indian standards, modulus is given as 5000 times square root of FCK. Please remember that this 5000 term actually comes about because of assuming a typical standard unit weight of the concrete. The unit weight of the concrete is typically 2400 kilograms per cubic meter. So, if you use that in this equation, you end up actually getting close to this relationship called 5000 square root of FCK. Again, this is only based on data which was generated long time ago. Several concretes today with modern materials may or may not satisfy the requirements suggested by this data. Okay, so if you are going to be designing new concrete for a particular building, especially for high rise buildings where modulus is extremely important, it is always better to get the modulus tested rather than rely on this equation, which can go horribly wrong, especially with the modern day high strength concretes. Okay. So, the dynamic modulus is the modulus which we find from other tests, not loading based tests like ultrasonic pulse velocity, like resonant frequency. There are different tests from which you can actually measure the dynamic modulus of concrete. Now, those kinds of testing give you moduli values that are much greater than what you get from static tests. Okay, please remember that. For most concrete, modulus is between 15 and 40 gigapascals. Okay, for very low strength concrete, we are close to 15, and for very high strength concrete, we are in the range of 40 and above. Poisson's ratio, once again, can be measured in the same experiment as your modulus of elasticity. Again, you need to affix strain gauges in lateral and axial directions. Please remember, when you talk about axial in the case of a cylinder, we are looking at circumferential change. Okay, so you have to use the right kind of equipment, right kind of monitoring to determine these values, and obviously you can calculate your Poisson's ratio as the ratio of the lateral strain to the axial strain. For most concretes, Poisson's ratio is between 0.15 and 0.22. And again, you all know from basic mechanics that the Poisson's ratio is related to the Young's modulus and the modulus of rigidity by this equation. So, when you have two of these parameters, you can calculate the third one and get most fundamental critical properties of your concrete. Now, before I get on to the next stage, I would like to stop for a few minutes and ask you if you have any questions at this stage, so that we can understand this and move forward to the next segment, which can be a little bit more difficult to understand, because we are trying to understand how the stress strain characteristics of the concrete are actually evolving, and why we should actually make measurements on the stress strain response also and not just on the compressive strength. Okay. So, I will stop this presentation briefly, maybe about 5 minutes, and ask you if you have any questions at this stage. Okay, there is a question about explaining direct tension. Okay. Now, direct tension is nothing but the same uniaxial tension test that we typically conduct for steel, right. For steel, what do? We have this steel rod which we grip between the grips of your machine and simply pull it off in direct tension, right. We are simply applying direct tensile loading in this case. In the case of concrete, as I told you, because of the presence of aggregate, you have to have specimens that have certain minimum dimension. So, designing right kind of grips to hold such concrete at the ends to pull apart this concrete in tension could be quite tricky, because of the amount of force that you apply at the ends to grip the concrete. There may be some crushing that may happen even before the tensile failure of the concrete. So, direct tension test in concrete can be quite cumbersome and difficult to set up. I am not saying it is impossible, definitely possible, but most labs will not have the capability of doing this. Okay, there is a question which says, if the cube strength is 25% more, why do we use only 0.8 times FCK? Yes, see again, cube strength is equal to 1.25 multiplied by cylinder strength approximately. So, cylinder strength is equal to 1 divided by 1.25 times cube strength. So, that is why 1 by 1.25 is 0.8, right. So, 0.8 times FCK is what we use as a measure of the compressive capacity of the concrete when we calculate the total compressive load that the concrete column can take, right. So, 1.25 is the ratio of the cube strength to the cylinder strength. So, if you want the cylinder strength, you take the cube strength and divide by 1.25. In other words, you multiply it by 0.8. Okay, maybe you can have more questions in the next segment, which is going to be a little bit more difficult. So, let us move on to that segment, and I will give a break again so that we can talk about what the different aspects are. You can ask your questions at that stage also. Okay. So, let us get back to the presentation. Alright, so please recall the drawing that I had shown you earlier regarding how the concrete actually cracks. I will go back to that drawing in just 1 minute. So, that is the schematic suggested by most people as to how concrete actually cracks and how the cracks grow into causing failure. So, yeah, at very low load levels, you have cracks around the interface. These cracks start growing at slightly higher load levels, and then they start propagating into the surrounding matrix, and then you have a large network of cracks that gets created, which then ultimately causes the failure. Okay. So, now if you really look at it, the same thing has been plotted here. You have the stress versus strain. In the beginning, you have the negligible bond cracks, then you have the growth of bond cracks, and then the bond cracks start growing into the matrix, and finally you have a very fast growth of matrix cracking, which leads to a complete disintegration of your specimen. Okay. So, now if you think about it, if you look in the stressed strain diagram, most times what do? We take the compression, we take the tube or cylinder in the compression machine, we load it until it fails, and that is all, we leave it. Okay. But what we do not understand is what really happens near the top stage where the cracks have all joined together. How are they actually opening up to cause failure of the specimen? Now, for that we need to do our test in a slightly different fashion, and that is what we will talk about in just a minute. So, if you look at this, the stress versus strain relationship for concrete truly actually looks like this. You have this increasing stress region, you will go to the ultimate stress, and then what you start seeing is that with increasing levels of strain, your stress actually starts falling. That means your material is undergoing what we call as strain softening. Now, this is something quite opposite to what you might have heard about in steel, where we talked about strain hardening behavior that occurs after the plastic flow has happened in your mild steel, right. So, what is happening here? You have your ascending branch where the stress is increasing with strain, you reach the ultimate load, and then the stress actually starts reducing beyond that point. Now, what does this mean to say? What we are trying to say is, in the ascending branch, the cracks are growing, okay, and you start forming some sort of a very large set of cracks here, or we call that as a crack band. Now beyond this point, what is actually happening is the specimen does not have any capability to take extra load. On the other hand, because the aggregates are still interlocked, even though the crack has appeared, the aggregate is still interlocked. It takes some time before that crack actually grows into a larger crack, which causes completely failure of the specimen. Now obviously the load carrying capacity of the concrete at that level of cracking is going to be substantially lower. That is why you start seeing this falling branch. That means after the ultimate load, your stress actually lowers with respect to the strain. So this extra bit of resistance against complete failure or complete collapse comes about because of friction and interlocking between the cracked sections. You can imagine concrete has a lot of aggregates, the crack is not perfectly straight, right? The crack is going round and round the aggregates, so there is a lot of jagged edges and all that. So a concrete cylinder that is going to be crushed does not completely fail or fall apart until the crack in between grows into a much larger extent of cracks. Okay, so that's why you see that your concrete takes a long time before it actually completely falls apart if you use the right kind of machine. If you are using a typical load testing machine, all your concrete will do is you take it to the ultimate load, it will simply collapse after that. Okay, but then to get this descending branch, we need to do the test in a slightly different manner. So once again, just to show you this strain softening behavior in concrete, you again see the same sort of diagram here. There is minimal ITZ cracking at very early stages. As you increase the load further, you start seeing that your aggregates, the zone around the aggregates, the cracks have developed more and more. If you reach from 70 to ultimate stress, these cracks have formed a localized band. Okay, you see this is the localized band of cracks that is formed. Now for complete collapse to occur, these localized cracks have now got to open up. Okay, how is that opening up happening? When the friction between the materials of the concrete is getting overcome, these cracks are now opening up. So beyond a certain stage, there will be absolutely no friction to keep the material intact, and that is when your complete failure will happen. So that is called localization of cracks, and finally the crack opening that leads to the failure. That is your crack opening that is happening. Okay, this is again showing you a very similar concept of localization. As I told you, when you are testing a cylinder, there is a zone right in the center where you feel a proper compressive loading. Okay, so the crack that we showed here will actually form in the central part of your cylinder alone. So it will start forming at the central part of your cylinder. So all your cracks will be localized close to the central part of your cylinder. Okay, that is why you are getting a relationship which is similar to this. Okay. Now what happens when you increase the strength of your concrete? We earlier discussed this. I said that when you increase the strength, the cracks tend to go through the aggregate rather than around the aggregate. What does that mean? That means that your concrete is getting more and more brittle. The concrete is getting extremely brittle. So in other words, the ductility is reducing, or the area under the stress strain curve is actually going to go down when you increase the strength of your concrete. So this is a concrete which is of low strength. As you keep on increasing the strength, you see that after you reach the ultimate stress, there is a sudden failure. There is no more gradual failure. At lower strength levels, after the ultimate stress, there is a very gradual approach to failure. Okay. So in other words, what we are trying to say is, when you increase the strength of your concrete, the material becomes more and more brittle. It has a higher elastic modulus, but you ultimately end up producing very little strains beyond the peak stress. Okay. So why is this post peak response important? What are we trying to do with this? For conventional structural elements, we don't even think about what happens to the concrete. We assume concrete is cracked already, or when we take the capacity in compression, we take the 0.8 times FCK, whatever it is. So where does it come into play that this strain handling capacity of concrete is important? Ductility of concrete, where is it important? That gets important when we talk about special concretes like fiber reinforced concrete. Please remember, I talked to you earlier that fibers generally tend to bridge the cracks and prevent the cracks from propagating or opening up. Okay. So if you compare, on the left here you have comparison of a normal concrete and high strength concrete. So what are you seeing here? The peak stress or peak load is increasing, but what happens beyond load is you have a sudden drop in the load, okay. There is no gradual release of the energy. In the case of fiber reinforced concrete, that is something different. If that is your normal concrete, which is represented by the dashed line after the peak has been reached, the dark line shows the fiber reinforced concrete. Now what is happening is, in effect your strength is not really enhanced by a tremendously high amount. You may get some enhancement in strength depending upon the size of the fiber, but what you get for sure is that after the peak load has been reached, the failure takes a very long time to happen when you have fibers inside. Now that is only natural, right? When you have a wound on your body, you put the sutures. What is the function of the sutures? They prevent the wound from opening up so that there is some healing that takes place. Similarly, fibers that are bridging the cracks ensure that the cracks do not open up very fast and have a very gradual opening to failure. So the fibers prevent the cracks from growing to failure suddenly, and they have a very gradual opening of the cracks towards failure. So fibers help in improving the post peak response of the concrete and make concrete more ductile. Now where are the applications again? Examples where you need good post peak response of concrete could be industrial flooring, where you need very good impact resistance from the floor. This could be from blast resistant structures, okay. For example, when you have bomb shelters or bunkers that are made with concrete, if you make with fiber reinforced concrete, the capacity to take up dynamic loads which are created because of that kind of effect is much better. Even an earthquake, you can have much better response of your concrete if you have fibers inside because of this extremely high post peak load carrying capacity of the fiber reinforced concrete. Now how do we measure this post peak response? I will give you, without getting into the details because they may be requiring too much time, I will go into two simple techniques. I am saying simple on paper, but actually to do this in the lab can be quite a difficult exercise. To how to obtain the post peak response of a concrete. One way is to actually use some sort of a composite specimen. What is this composite specimen? You have a concrete cylinder in the center and you have a steel ring around the concrete. This is a steel ring which is of the same height as the concrete specimen. So that is surrounding the concrete. It is not touching the concrete, but it is simply surrounding the concrete, so that when you load the concrete, the steel ring also gets loaded at the same rate, okay. So now what will happen? You need to measure for the applied load what is the deflection of the composite, that is steel plus concrete combined, because that is your entire material system that is getting compressed, okay. So that is a stress deflection diagram for the composite. Now for the levels of load that this composite will be able to take before concrete completely fails, the steel is obviously a very high strength material as compared to concrete, so it is still going to be in its elastic region for that level of deflection, okay. So when steel is in its elastic region, you can calculate the stress in steel by understanding what the strain is. In other words, you can calculate the stress for a given deflection and that will be a straight line. This red line is basically the stress deflection response for the steel, because for the levels of load which we are going to be subjecting the specimen to, the steel will still be in elastic range, elastic limit. So now you have the composite response and you have the steel response. So you subtract the steel response from the composite response, you will actually get the stress strain relationship for the concrete, okay. So here we have used some sort of an indirect method. Rather than loading concrete directly, we have loaded it along with the steel ring on the side, on the outside, and then we are trying to measure the overall response by subtracting the steel response from the composite response, okay. So that is one method of actually getting your stress strain relationship for concrete. The other method, which is the more appropriate method and more popular method, is what we call as closed loop testing with displacement control. Now what do you mean by closed loop testing with displacement control? Please remember, most of our machines are load controlled. We keep getting more and more increment of load to the specimen. So if you look at it, that load versus displacement diagram, the typical machines have increments of load given to the sample or the specimen. So you have the load which is increased here, increments of load which keep on going, and at the point where you reach the ultimate load, you cannot give even a small bit of extra load, because at that point failure will occur and your concrete specimen will totally disintegrate beyond that point. Now we know very well that in truth that is not what happens. We get some sort of a post peak behavior. To get that behavior, what we need to do is control the displacement of your specimen. So here we were controlling the load, here we are going to control the displacement. So instead of loading, we give or we measure the displacement that has been undergone by the specimen, okay. So in the beginning, in the ascending part of the branch, we are giving small increments of load and measuring displacement. But what happens now is we want to maintain the same level of displacement each time. Each time we give the same level of displacement. How do we do that? So what we see is to give a certain level of displacement, what is the load required? Okay. So you know that when concrete starts cracking, it will get more and more displacement. Displacement will increase when concrete starts cracking. So what we try to do is reduce the rate of loading at that point. When the displacement increases tremendously, we reduce the rate of loading. So for the same increment of displacement, what I am trying to do is now I keep measuring my load. So what will happen is even after I reach this failure load, what's going to happen is for increasing displacement, I can now produce it with a smaller load. So I start reducing my load here and come to the descending branch of the curve. So this way I am able to get a complete stress strain response, and obviously failure will happen when my specimen is no longer able to hold up the width of the crack that is appearing. Okay. So sorry, I'll come back to this. So that's your specimen that is being loaded. You're measuring the load using the load cell. You have the actuator, which is actually the piston which is giving the load to the specimen, and the actuator is controlled by what we call as a servo valve. Okay, now you're measuring the displacement of your specimen, and that displacement is being sent as a feedback to the servo valve. So it tells you that, okay, for the same displacement now, you have to open up the, or you have to pump the piston only by a certain amount to ensure that you get a different load this time, which will give the same level of displacement. Okay, so you have a feedback from this length measurement device which is being sent to the controller, and the controller now tells the servo valve to apply a load which is equivalent to a smaller load level, which will lead to the same level of displacement. Okay, so now you are able to get, without failing your specimen, a complete stress strain response, and you can calculate some sort of a parameter like the toughness or ductility by measuring the overall area that you have under this graph. The area under the graph is basically your ductility of the system or strain energy released in the system. Okay, so using this, what we can find out is that the stress strain relationship for concrete is mostly linear up to about 30 to 40% of the load. Then you have a major non-linearity, and this non-linearity, as I mentioned earlier, is because of the heterogeneity of concrete, primarily the influence of your interfacial transition zone and the micro cracks that may be present in your concrete. We generally assume that for normal concrete, the strain corresponding to ultimate stress is about 0.003. Now that can be quite different when you change the grade of the concrete. What turns out in concrete is that the behavior and tension, in terms of the non-linear stress strain behavior, the behavior is similar. Obviously the strengths and strains, stresses and strains and tension are going to be much smaller as compared to the stresses and strains in compression. Okay, that's what you need to remember, that the overall shape of the stress strain curve will be similar, but the values of stresses and strains will be quite different in the case of tension. Again, this is an example presented from the book by Neville. So there are two stress strain relationships presented here. One is for a normal weight concrete. You can see the dark circles here, and you also have the ones for lightweight concrete, which are the open circles. Okay, so you have two different types of concrete for which the stress strain diagrams are given here. Lightweight concrete is definitely a lot more deformable because the aggregates are not very strong in that case. So because of which it is able to take much higher strains. You can see that the strain at peak is much more than the strain at peak for normal concrete. And then you have the descending branch. You see that the stress dissipates very slowly, the crack grows until a level of cracking has been reached where the specimen is no longer stable. So just to summarize this section on post peak behavior, in metals we come across the phenomena called strain hardening, where after yielding and after the plastic deformation has happened, the material actually undergoes an increase in stress with increasing strain, that is called strain hardening. In most models for different types of ductile metals like mild steel, we assume an elastic plastic relationship in which after yielding we assume that there is straight flow of the material, that means absolutely no increase of stress with increase in deformation. In concrete we have what is called the strain softening behavior, in which after we reach the peak stress, the stress actually starts reducing with an increase of the displacement of your concrete. Okay. In the case of very high strength concrete, or in the case of materials that are extremely brittle like chalk, you have what is known as a brittle behavior, where after the peak or after this point has been reached, there is no additional deformation and the material simply directly collapses, and that is basically your ultimate strength. The yield strength is basically equal to your ultimate strength in that case. So, because of these complications, we generally do not talk about a yielding point for concrete, because concrete is not yielding specifically, it is deforming and slowly collapsing when the cracks in it start growing to a level which is not manageable. Okay. So, I was talking about the fact that you can use this information from the post peak behavior to calculate some important characteristics from of the concrete, like the ductility. Now, a very important characteristic within this ductility is the toughness of the concrete. Toughness is a measure of the ductility and it corresponds to the area under the complete stress strain curve. Okay, now we have looked at basic mechanics before. When we talk about materials like metals and all that, we measure the area under the stress strain curve, and we have the area until the elastic limit. We call that as a modulus of resilience, right. You might remember that we also say that the area under the entire curve is called the modulus of toughness. Similarly, in concrete also, the area under the stress strain curve can represent the toughness of the concrete. Now, as I told you, the importance of the post peak behavior comes into play only when we deal with special concrete such as fiber reinforced concrete. And because fiber reinforced concrete or fibers have the tendency to actually prevent the growth and propagation of the cracks, they tend to increase the level of deformation that the concrete undergoes before failure. Okay. So, I am going to give you an example as to how fiber reinforced concrete was able to increase the toughness of your concrete. Okay. So, here I am describing to you an experimental study that we did at IIT Madras. We chose a very brittle system, a high strength concrete was chosen in this case, and we used different types of fibers as fiber reinforcement for the concrete. We used polypropylene fiber, polyester, glass and steel fiber, and the total volume fraction that we had for the fibers was 0.5%. Now, you can imagine that fibers are dosed in concrete up to the level at which they don't cause much workability problems, because fibers can cause a lot of workability problems if they are not at the right size. Okay. So, 0.5 volume percent of the concrete was fiber. So, in the case of steel fiber, for example, 0.5 volume percent means 0.005 cubic meter. If you multiply that by the density of steel, which is 8,000 kilograms per cubic meter, that means approximately 40 kilograms of steel fiber were used in the case of the steel fiber mix. Of course, the densities of other fibers are going to be quite different. So, based on that, you have different dosages that were added to the system. Now, the hybrid combinations were also used in this case. So, what we did was, apart from just using steel or just using the polyester or polypropylene fibers, we also tried mixtures of these fibers. Now, why is that important? You know that steel fibers are extremely stiff, steel is an extremely stiff material. So, the post peak loading is where steel fibers will become very effective. On the other hand, at very early stages when the stresses are very low, there is some resistance to cracking that is desired. For example, we know about phenomena such as plastic shrinkage cracking or sometimes thermal cracking, which may appear very early in the concrete's life cycle. We are talking about few hours to a few days within the concrete pouring. Okay. Now, these cracks, there is no point in having steel fibers there, because steel fibers are not really effective at such low stress levels that are resulting in cracking for plastic shrinkage, right. In those cases, polymeric fibers like polyester and polypropylene could be quite useful. Okay. So, in that case, one would really benefit from using a combination of these polymeric fibers and the steel fiber. So, we also tested here the combination of steel along with polypropylene or polyester fibers. So there were several different studies that were conducted in this. One part was to understand how the fresh properties get changed. The other part was how the shrinkage cracking gets altered with the help of fibers, and the third part was to look at toughness of the material or the flexural and compressive toughness of the material. So the concrete mix design is presented here. As I told you, we chose a high strength concrete mix which was expected to be brittle. Okay, we had a water to cement ratio of 0.4, and the cementitious material also involved silica fume at a certain dosage. This concrete gave a compressive strength of about 65 megapascals at 28 days. These were the different fibers used in the study. We used hooked steel fibers, glass fibers, polypropylene fibers that were fibrillated. You can see the fibrillation in the polypropylene, and then polyester fibers. So these are the different properties of the fibers. As I told you earlier, steel fibers have a very high elastic modulus, okay, because of which they are effective primarily at very high stress levels. Okay. Tensile strength is also relatively high as compared to polypropylene or polyester, but glass fibers can have a higher tensile strength than the steel itself. However, if you compare the sizes, it could be quite different. Lengths of the fibers for hooked steel is 30 millimeters, polypropylene is 20. Glass is only 6 millimeters, that means they're extremely short fibers, and polyester is about 12 millimeters. Diameter of the fiber is 0.5 in the case of steel, and 0.1 for polypropylene, 0.01 for glass, and 0.05 for polyester. Now you can imagine that when the length to diameter ratio is very large, it depicts a better holding capability of the fiber. Okay. Only thing is, even if the length to diameter ratio is large, if your tensile strength is going to be small, then there is a chance that the fiber may actually rupture before getting pulled out of the matrix. Okay. So you need to be careful as to how you do this test. Okay. So let's look at the different fiber dosages. As I said, overall the dosage was 0.5% by volume of the concrete. In some cases there were mixtures of steel and other types of fibers together. And this is how we actually did the experiment. So this was your beam, the fiber reinforced concrete beam that was loaded in third point loading. So you see this is L by 3, that's also L by 3, that's third point loading, and we measured the displacement of the specimen right under the load. Okay. So this is the point at which the displacement is measured. We also altered the setup in such a way that we could measure the displacement which may be happening at the supports also, so that we actually get the net displacement at the center and use that for our calculations. Okay. You can expect the supports may also slip and have some displacements. So we measure those displacements also and subtract those from the actual displacement that the specimen undergoes right in the center, right under the load. Okay. So these are the results that have been plotted here. On the top left, you have the typical load deflection plot. Okay, load on the y-axis and deflection on the x-axis. So you can see here for the plain concrete, the load deflection plot does not show much post peak behavior at all. So there is failure almost immediately after your failure peak load has been reached. Okay, there is failure almost immediately after the peak load is reached. It is interesting to note that for most of the fiber systems, the peak load itself is also increased. You see that the peak load also increases, that means there is a marginal difference in the flexural strength also. Okay, there is a increased flexural strength. But what is interesting to note that after this peak load has been reached, it is a very gradual failure. Failure does not happen suddenly like in plain concrete. You have a gradual failure for the fiber reinforced concrete. You can see here there is a gradual approach to failure, and by the looks of it, this red dotted line seems to indicate the best post peak behavior, and that red dotted line is nothing but the mix with the plain steel fiber. All the others are mixtures of steel with other types of fibers, and you can see that the steel fiber alone actually is able to perform much better than the mixtures with other fibers in the case of hardened characteristics or mechanical characteristics. Okay. So again, as we increase the steel fiber as we increase the replacement of steel fiber by other fibers, you see that your flexural toughness, that is the area under the stress strain curve, keeps reducing. The reduction in the area under the stress strain curve with increased level of non-metallic fiber, that means replacement of steel fiber. Nevertheless, for plain concrete, you are at a region of which is somewhere very low. On the other hand, even with the plain non-metallic fibers like glass fiber or polypropylene or polyester fiber, you are at a level which is much higher than that of plain concrete. Okay. So even if you do not use steel fiber, you still get a flexural toughness that is almost double or triple that of plain concrete. But in the case of steel fiber, you end up getting a much higher flexural toughness as opposed to plain concrete. We are in the zone of about 20 to 22 in this case. Okay. So which is almost 10 times better than that of plain concrete. So the toughness can be significantly higher for fiber reinforced concrete systems, but you need to have a method of measurement of this toughness, and that is what I was trying to get at. As I told you earlier, toughness can be measured either using the flexural setup that we talked about just now, or you can also use a compressive or impact setup to determine toughness. In a compressive setup, you have a compression test going on here. That is the compressometer I talked about earlier, that is typically used for modulus of velocity, but you can also use it to determine the strains or displacements when your load is being applied and determine the load displacement curve based on that. So that is actually a compressive toughness setup. You do the same thing, you do a displacement control and you end up getting the compressive toughness also in this case. Now you can also determine fracture energy or impact cracking. So here the impact is mostly determined by using a disc shaped cylinder which is placed here, and there is a weight, about 4 kilogram weight, which actually is guided through this tube to go and directly fall onto the concrete surface. So you can imagine that for a plain concrete, after a certain number of times that this weight falls on the concrete, there will be cracking, and as soon as cracking appears, there will be complete failure of your specimen. In the case of fiber reinforced concrete, even after the cracking appears by falling of your weight on top, this crack will take some time before it actually disintegrates the specimen, right. That means that even after the first crack has appeared, I can continue to drop the weight several number of times before the fiber reinforced concrete actually fails completely. Okay. So impact testing can also bring out the benefits of fiber reinforced concrete. Now this is an example of how we applied the stress strain characteristic, how we applied the post peak testing to determine the stress strain characteristics of heavyweight concrete. Okay, this is an example of heavyweight concrete. Now heavyweight concrete is something which has a density of more than 3.6 gram per cc. Please remember the density of normal concrete is 2.4. So here we are talking about 1.5 times that or more density than normal concrete. Okay. So where do we use high density concrete? We generally use it wherever we need radiation shielding, especially nuclear reactors. Okay. Or when we need some very heavy masses, for example for offshore oil platforms or for dry docks for instance. Okay. So in those cases we need massive weight, so density is very high. So again we had done this test where we developed high density concrete with aggregate which were made with steel and with hematite, and these heavy density concretes were tested for their stress strain response under compression, and what you see very clearly is the ascending and descending branches of the stress strain response, and that is how we were able to actually complete this measurement by actually understanding how to do a displacement control of your concrete. Now this is again an example from the same project on high density concrete where we were determining the elastic modulus. Please remember earlier when we talked about relationship between elastic modulus and strength, I told you that the 5000 square root of FCK comes about because we assume normal density for concrete, that is 2400 kilogram per cubic meter. Now what happens if the density changes? Obviously that equation will not hold good. So what we have shown here is a model to calculate density of high density concrete or density of any concrete given its unit weight is different from your normal weight concrete. So here what is plotted is the modulus of velocity against the density to the power of 3 by 2 multiplied by the square root of strength. Please remember this is the same equation or same form of equation that was used by ACI to develop the original equations. Okay. So now this is the relationship between modulus of velocity and square root of compressive strength multiplied by density to the power of 3 by 2. You see that you get a fairly good linear response. What I have also plotted are the confidence intervals for the slope of this response. That means you can use this linear response with a fair degree of accuracy to predict the modulus of velocity of high density concrete from its compressive strength. There are some questions, you can talk about the responses to these first. So first question is, can jute also be used for strength improvement of concrete? Now please remember, jute is contributing essentially natural fiber, right? You have natural fibers, different types of natural fibers. So some different natural fibers can be used in concrete, but please remember that fibers don't essentially contribute to strength of the concrete itself, especially compressive strength. There is not going to be a major enhancement when you put fibers inside. Let's come back to the same issue, that fibers are not essentially used for strength increase in the concrete. Fibers are essentially important for improving the toughness properties, that is the post peak characteristics. Once again, just to explain this system a little bit better, maybe it will be good if I can draw this on the board and explain this again. As I was mentioning earlier, fibers tend to bridge cracks that are there in the concrete. So if you think this is a very large crack that is present in the concrete, and if you have fibers that are sufficiently present across the crack, they will try to bridge the crack. That means they are preventing the cracks from opening up or propagating. Okay. So how is this going to contribute to an increase in compressive strength? Please remember again, the strength was determined by the growth of the cracks at the interface and how these actually coalesce to become larger cracks and ultimately led to failure. Now if I have my interface which is going to crack, my fibers at that level of, or at that size level, may not be effective enough to actually control the growth of the interface cracks at all. Okay. Similarly, when you look at a fiber, when you look at a flexural concrete, flexural test on the concrete, the crack is going to be produced at the bottom fiber of your beam, right? If you are having a beam that is going to be bending, okay, if you are applying a midpoint load, your crack is going to start propagating from this point onwards. Now, how is the presence of the fiber going to help in the improvement in the tensile strength of this kind of beam? It's probably not going to happen that way, okay. So what we have instead is the fibers actually start getting effective only after the cracking happens, because unless this cracking happens, the fibers will not be revealed properly, right. So once the fiber becomes active after cracking happens, it starts bridging the fibers, it starts bridging the cracks and prevents the crack from opening up. So any type of fiber, let it be steel fiber, let it be natural fibers like sisal or jute, or let it be polymeric fibers like polystyrene, polyester, all those different types of fibers, they are not essentially going to lead to a major increase in your strength, but they are going to improve the load carrying characteristics after cracking has appeared. Okay, especially steel fiber is going to be most effective, but yes, jute fiber and sisal and other natural fibers can also be effective, but never to the extent of steel fibers. Okay, so the question is, why concrete is strong in compression and weak in tension? Okay, now that's a very important question, and that basically is the fundamental characteristic of the concrete itself, that it's strong in compression and weak in tension. Again, to answer this, you must think back to the original discussion that we had about concrete being a two-phase material. Okay, you have your concrete, which is basically cement paste phase, in which you have aggregate phase that is getting dispersed. But what we also should remember is that concrete has a lot of pores in it. Porosity in concrete plays a large role in determining its response to compression or tension. So when these pores are present, the pores are what contribute to lowering the strength, because that's the part of the volume that is not occupied by solid. So you have air filled gaps which are present in the concrete. Further, you also have interfaces between your paste and aggregate. I told you earlier that paste and aggregate are two dissimilar materials which have a very large mismatch of their engineering or elastic properties. For example, the modulus of elasticity of the concrete aggregate is much more than that of the paste itself. Okay, so you have a major mismatch between concrete and paste, aggregate and paste properties, which leads to a very weak interface. Now, while this interface comes into play as far as compression is concerned only at a late stage. Please remember, I told you that with growth in the level of load, with the increase in the level of load, the cracking in the interface slowly grows and ultimately develops into a larger network of cracks that are completely causing the collapse of the system. In the case of tension or in the case of flexure, the mode of cracking is going to be quite different, and there we are talking about the separation of these interfaces or the paste from the aggregate. When you are causing the separation of the paste from the aggregate, that effect depends a lot on the bond between the paste and the aggregate. In the case of compression, that is not as critical as in the case of tension. So, because of this major mismatch in the paste and aggregate, and because of the fact that the interfacial zone is already cracked in the system, you essentially have a much poorer response in tension than in compression. So, concrete becomes much stronger in compression than it is in tension. Now, one more question is, when cylinder strength is more accurate than cube strength, why is cube strength referred with regard to grade of concrete? Okay, now please remember that cubes are used in our country for determination of compressive strength of concrete. There are several countries that actually use cylinders. Okay. Now, why is the cube used? The cube is basically used because there is a much more easier way of testing cubes than cylinders. Just imagine, when you have a cube, you are filling up the cube, totally there are 6 faces in the cube, and when you are filling up the cube, 5 of those faces are against the mold itself, right, are sitting flush with the mold, because of which you have a very good finish on 5 surfaces. Only on the 6th surface we are basically trying to finish using a trowel. Okay. So, all you need to do is take this cube, turn this by 90 degrees and load it into your loading machine, put it into your loading machine, and the loading platens are now in contact with the 2 faces that are properly finished, which do not have any influence of the trowel finish. Okay. So, cylinder is much easier to test rather than a cube is much easier to test than a cylinder. You do not need any preparation, you just turn it by 90 degrees and put it inside your machine. On the other hand, in the case of a cylinder, one part of the cylinder, that is the bottom of the cylinder, is properly finished, but the top part of the cylinder is where you have the trowel finish. Now, if you put this directly into the machine, your concrete load distribution will not be uniform because the surface will be uneven. To make sure that the surface is even, you need to grind it or cap it or have a some sort of a unbonded cap that is placed on top of it. So, it becomes a lot more cumbersome to test cylinders as opposed to cubes. Cubes are much easier to test. You cast them and you turn them by 90 degrees and simply test them. In cylinder, you need to prepare the surfaces properly for testing. So, that is why cubes are preferred in several countries. On the other hand, cylinders are also used for testing in several other countries. Okay. It is just a choice that we have had in India that we prefer cubes. Essentially, the British system is also something that prefers cubes. So, given that we have taken over several of the practices that were done by the British, we are still testing cubes. If you go to the US, for instance, they test cylinders. Are there any more questions from the audience? Our next segment will be on durability testing. So, I thought instead of starting it off today and giving you some confusion with respect to hardened concrete and durability characteristics, we will take up durability separately in the lecture next Monday. So, we still have sufficient time in this session. If you think you have some questions that are dealing with what we have talked about just now, or even what we covered in the first lecture last Friday, that was on fresh concrete properties, please do ask your questions now. Okay, all right. In that case, if there are no more questions here, you can always ask me the question next time when I come on Monday next week. That is on 19th, when we have the third session of this module on testing of concrete. We will essentially talk about durability testing in that module. If you have further questions, you can ask me at the beginning of the class on 19th. As for the session today, we essentially talked about how hardened concrete is tested primarily for its compressive and flexural strength, and also its response to loading to determine the stress strain characteristics and to understand fundamental constitutive relationships. We also discussed about a very important parameter called toughness, which becomes important when we deal with special types of concrete like fiber reinforced concrete, because that's where we actually get a good sense of how the concrete would resist deformation before it actually fails. Okay. So thank you all for your attention for today. We will get back to you on Monday 19th with the third segment of this module, that's on durability testing. Thank you.